And it is time to start Unit 7. Unit 7 is the longest and hardest unit, I think, of second semester. So our unit test will actually be 2 days. We'll have the non-calculator part first and the calculator part second. That, of course, won't be for quite a while yet. There's a lot of new stuff in here and a decent amount of algebra that's going to maybe cause you some consternation before we then get to functions of exponents and logs. So if you take your time and you take the little quizzes as we go along and just build your confidence, you will be able to do it. I apologize for the banging and the loud noises off in the distance. There is some construction outside of my window. Alright, so the first part of this should be review for most of you. There is a handout that you will that I have for you. So if you would pause and get this handout, I will pull it up, the Word version of it, and we'll take some notes on here. So I know some of you, especially those of you that think, oh, I know all this already, are going to be annoyed by the fact that I make you take these notes, but I am going to collect these. These notes are going to be collected and checked for all the vocabulary, because I do believe in it. Okay? I believe that what I'm going to make you write down, you may think, oh, I already know it and I don't need it, but it's going to help you in the future. I promise. Alright, so in the expression x to the n, some vocabulary that you probably know. X, the big number, is called the base. But we are going to say the base is an element of the real numbers, although we'll be dealing mostly with rationals. But the base cannot be equal to 0. And if you remember, exponentiation is just repeated multiplication, right? I mean, what is repeated addition? Right? 3 plus 3 plus 3 is 9, or plus 3 is 12. And you can write repeated addition, but repeated addition of the same number is also, right, 3 4 times, right? So this is just a shortcut way. Well, what is 3 times 3 times 3 times 3? Repeated multiplication is written this way. 3 multiplied by itself 4 times, right? 3 times 4 is really 3 added to itself 4 times. When you multiply, it's 3 multiplied by itself 4 times, right? Repeated addition is actually multiplication. Repeated multiplication is exponentiation, right? But multiplying by 0 is problematic. So, I mean, it's great in a lot of instances where multiplying by 0 makes things go away, but when we're dealing with exponents, we don't really want things to go away. So we are going to say that our base is not going to be equal to 0. And of course, I've already used the vocabulary that the little number is called the exponent. And we have no restrictions on our exponents. Okay, so for this list of numbers down here, I'm going to highlight yellow all the bases. So, of course, 2 is the big number, 2 is the big number. Now, look at this. If I highlight 2 or 2x, that's incorrect. And this, I know, might sound silly, but this is a common mistake. The base, the Aunt Sally matters, right? You do exponents before multiplying. So the exponent of 7 is on x, not on 2. The exponent of negative 7 is on x, not on 2. Here, with grouping, because grouping symbols matter, the base is now 2x, and 2x has an exponent of negative 7. Here in this expression, 3x is the base with an exponent of 2, but 4y is not the base. Only y is the base with the exponent of 2. 7 is the exponent. 7 is the exponent. Negative 7 is the exponent. 7 is the exponent on x. Negative 7 is the exponent on x. Negative is the exponent on 2x. 2 is the exponent on 3x. Y is the exponent only on y. I mean, technically, I don't want to leave these guys left out. This 2 does have an exponent with it. It is a base, but its exponent is 1. This 2 is a base. Its exponent is 1. This 4 is a base. Its exponent is 1. Right? Alright. So properties of exponents. There's really proofs behind all of these properties. And the important thing about properties that we often forget because we so often move from left to right is that we forget that a property goes both ways. There are lots of times when I see an expression this way and I want to rewrite it this way. And you probably remember this rule from Algebra 1 or pre-algebra. But there's going to be times, trust me, when I see an expression this way and it is useful to write it back with 2 bases. So here's the language that I want you to write in here. If I see the same base twice, polite pause, with multiplication in between them, then, this is really an if-then statement. If I see the same base twice with multiplication in between, then I can write the base once and add the exponents. Multiplication in between, we've added the exponents. But again, that's of the same base. So here, if, then, and I bet you can write this, if you see the same base twice, with, polite pause, with division in between, then you may, you don't have to, but you may write that base once and what? Subtract the exponents. Division in between, then you subtract the exponents. So of course this expression can be written this way. And it is numerator exponent minus denominator exponent. So, but again, don't forget that if I see an expression with one base and an exponent that can be written as a subtraction, if I need to, I can write a division problem. Here, notice, if I see the base only once and I see multiple exponents, then multiply those exponents. Keep that base and multiply exponents. Multiply said multiple exponents. So this looks like x to the a times b. But let me plant a little seed in your head here that multiplication, you've known for a long time, is commutative. So I could write this, if I chose, as x to the b times a, couldn't I? And then if I was going backwards, couldn't I write this as x to the b times a? Yeah, tricky. Rule number 4 is really just is the same rule as rule number 3 or property number 3. I just gave you different bases in here. but it really is the same thing. If you see different bases and multiple exponents, then keep each base, and I'm going to throw a D word in here, distribute the outside exponent. So here notice that I have x and y, which are different bases, and that x has an exponent, y has an exponent, and then there's an exponent outside the parentheses. Distribute, and again, distribute does, isn't that weird how that does that? Distribute is just a fancy word for saying multiply, right? So that's x to the AC, keep that base, keep the y to the BC. And again, think about my blue version up here. If I needed to, I could do a lot of things, right? I could write this as a to the C, x to the CA, y to the CB if I wanted to. I mean, there's just lots of different things I can do. 5 is a continue is that same rule because I have different bases, an x and a y. If you see different bases and multiple exponents, but division in between. Oh, I guess I forgot to write here, see different bases with multiplication in between, and multiple exponents. So again, here I have x as a base, y as a base, different bases, division in between, and x has an exponent, y has an exponent. And remember, everybody does always have an exponent, right? Everybody has an exponent. If you see any base and it looks like it doesn't have an exponent, it has an exponent of 1. So this can be, but division in between, then keep each base, and distribute that outside exponent. So that doesn't sound any different. But it just means you keep the division, right? Just like here we kept the multiplication. Here I'm going to keep the division, and it's x to the AC over y to the BC. And then again, remember that I can, if I see a fraction, I can, with the common, right, with a common exponent here, that if I need to, I can pull that common exponent outside, right? Alright, a base with a negative exponent. A negative exponent does not mean that you have a negative number. Just remember that. A negative exponent does mean reciprocate the base. Oh, I ran out of room here. Reciprocate the base and I need to erase so I can get some more room. Remember, all of these properties you don't have to use. You just use if somebody asks you to. Or if you need to. So, a negative exponent does not mean a negative number. Instead, a negative exponent says to 1, reciprocate the base, and 2, change sign of the exponent. So in other words, x to the negative n is really x over 1 to the negative n, right? So, a negative exponent says you can reciprocate the base and change the sign on the exponent. So the exponent was negative, make it positive. Now, of course, this can be written as 1 to the n, using rule number 5. This can be written as 1 to the n, but 1 to the n is always going to be 1 over x to the n. That's very handy when you don't want negative exponents. You can get rid of them this way. Of course, there are times when I have an exponent in a denominator that, notice, if I use this rule backwards, I can get an x, a variable, out of a denominator. I just have to deal with a negative exponent. So this is just, again, this is just a personal preference or just a rule preference for whatever test or homework assignment you're doing. Alright, property number 7. Any base. Any legal base, remember we have a restriction on our base. We can't have a base of 0. Any base to the power of 0 is 1. And I love 1. Now, the reason any base to the power of 0 is 1 refers back up to property 2. Remember, if you have, for instance, let's say if you have x to the a over x to the a, isn't that x to the a minus a, which is x to the 0? But what is anything over itself supposed to be? 1. So that's why x to the 0 has to be 1. Alright, lastly, x to a fractional power when that fractional power does not reduce to an integer. I mean, you can use it when the fractional power reduces to an integer, but it's just kind of silly. So, what do I do with a base that has a fractional power? Fractional powers are actually one and the same with radicals. Isn't that crazy? So, the numerator of your fractional power stays with the base. But the denominator becomes, and here comes a weird word, index of a radical. And I'll show you what I mean by that. It's actually a very cool and useful property. So I'm going to write it in here, what it looks like. So keep the base x, keep the numerator power, right? The numerator stays with the base, and the denominator becomes a radical. Well, not a radical, but you create a radical, and inside this little check, this is called the index. Right? That seems crazy. I'll give you an example. You all know what the square root of 25 is. But talk to me about the power on 25. right? Isn't there a power of 1 on 25? If you ever need a power, it's just 1. Well, that's because it's the most common power. You know what the most common radical is? The square root. Square goes with 2. There's actually an index of 2 in here on every radical. So the square root of 25 to the first is 5. Now let me use this property backwards. This means that the square root of 25 can actually be written this way. 25 to a fractional power, where the numerator was the power that you saw on 25, and the denominator was the index of the radical. And if you don't believe me, go ahead and type on your calculator 25 to the 0.5 power, or 25, you type this on your calculator, and you know what you're going to get? 5. Guess what 9 to the 1/2 is? Yep, that's the square root of 9, because there's 2 in here and a 1 on there, and you're going to get 3. Crazy, right? Here's a cool way, that's just kind of neat, but here's a cool way to use this when you don't have a calculator in your hand. Which I'm going to take away from you, by the way, for the first couple of quizzes. And you might stress out if I say something like this. Well, let's go backwards. What if I said to you, what is 3 cubed? Now let's make that 3 to the 4th. 3 to the 4th, right, is 81. Where's my pen? Right? Well, what if I said, what if I gave you 81 and said, what is 81 to the 1/4? Well, that's asking what number can you multiply 4 times and get 81? And what number is that? 3. Right? Alright. Let's go back to the PowerPoint. Once you've taken those notes. Oh wait, one more thing. I have to write a big no-no. To you here. Notice that you have an exponent outside of parentheses. This rule does not apply in this case. You may not distribute powers here like you did here. Why? That's right. The plus stops you. You may not distribute exponents across terms, only across factors. Factors. Alright, let's go back to the PowerPoint and do some couple of examples. Alright, so let's practice. Using some of those, the rules that I just gave you, let's practice here. Alright, so 17 has an exponent of 1, z has an exponent of 1, there's an exponent of 1 out here. So that's nothing but 17z. However, see the base, different bases with multiple exponents, distribute. Z to the 2 times 1 and z to the, 3 to the 2 times 1 and z to the 2 times 2. So this becomes 17 times 9 times z to the 1st times z to the 4th. Well, 17 times 9, that's a little bit annoying, but 17 times 9, you can do that, right? I think I did that right. 9 times 7 is 63. So combine these two into 153. But now what is this property? See the same base twice with multiplication between, write the base once, and add. Let's look at this one. You may not cancel this 5 and this 100. That's not a 5. What is that? That is an exponent of 1. See different bases with multiple exponents. Distribute. So this is 5 to the 3 times 1 and x to the 2 times 3 over, nothing happening here. But now what do I have here? This is 5 times 5 times 5 times x to the 6th over, what is 100? 100 is 5 times 20, or 25 times 4, and I have 5/4. And what is this? Now you can think of this two ways. You can think of it 6 x's up here and 6 5's down here. 6 x's here and 5 x's here, and all of them are going to cancel out except an x to the 1st. Or you can say that's x to the 6 minus 5, which is x to the 1st. Oops. Yeah. Let's use the commutative property of multiplication and multiplying fractions. And now what do you have here? See the same base with division in between. Write the base once and subtract. What is 55 minus 49? Another one, see the base twice with division in between, write the base once and subtract. 63 minus 55. And there you go. Now, I have a choice here. There is nothing wrong with distributing to this one, distribute, distribute, distribute to the one, distribute, distribute. Or I could use Aunt Sally, and I could work inside here first. I think I choose to do that. So all of this is to the 6th, but look at what I'm going to do. What is 10 divided by 5? What is see the same base twice with division in between, write the base once and subtract. See the same base with division in between, write the same base and subtract. So what's left in my denominator? It's right, just a 1. So now 2 to the 1st, p to the 9, n to the 2, all to the 6. Now I'll use my see multiple bases with multiplication in between. distribute. 2 to the 6 times 1, p to the 9 times 6, n to the 6 times 2. And yes, I expect you to tell me what 2 to the 6th is, right? Come on, 2 to the 5th is 32, so another 2 is 64. If that was 12 to the 6th, no, just leave that alone. But 2 to the 6th, come on now. Now look how purposefully I tried to call your attention to this multiplication, right? I didn't have to do that, but I tried to be very, very obvious that there's multiplication between these, which means that you have factors. And if you have factors, you can cancel. This is basically just fancy canceling. See the same base, 6, with division in between. Write the base once and subtract. Now, what about this? Can you do any rules with this? Is this c the same base twice? I don't think so. This is just 64 over 3. So what do I have here? 64 times 36 over 3. Don't multiply that yet, because 36 is actually 64 times 3 times 12 over 3. So yes, 64 times 12 is a little annoying, but hello. I did take elementary school. So without a calculator, 768. So this last one. Again, you have to take care of exponents first before you multiply. There was nothing to simplify. I just have a bunch of different bases and a whole bunch of different exponents. Distribute, distribute, distribute. A bunch of different bases, a whole bunch of exponents. 5 to the 4 times 1, a to the 3 times 4, b to the negative 2 times 4. 5 to the negative 2 times 1, a to the negative 4 times negative 2, b to the negative 5 times negative 2. Now I'm going to use c the same base, because I've got multiplication. Look what I have here. C the same base twice with nothing but multiplication. Write the same base once and add. 4 and negative 2 is 2. Done and done. See the same base twice with multiplication in between. Write the base once and add. Done and done. See the same base twice with nothing but multiplication in between. Write the base once and add. And of course, don't leave 5 squared as 5 squared. What are you going to write that? That was 5 to the 10th. Go ahead and leave it. But it's not. 5 squared. That is 25. Sweet. Annoying that they write division like that. I'm going to write it like this. And I'm going to look at my numbers first. And sure enough, guess what 1001 divided by 77 is? You know, if you have to, I don't know if I would give you something that, I mean, you could probably do it without a calculator. Well, I know you can do it without a calculator, but maybe it would take you a little bit of time. That is 13. Now, there's a couple of different ways, oh crap, a couple of different ways I could approach this problem. I can certainly use c the same base twice with division in between, write the base once, and subtract. Just be careful, subtracting is always challenging. This is negative 4 minus 6, which is negative 10. See the same base twice with division in between, write the base once, and subtract. Negative 3 minus negative 7 is 4. A perfectly acceptable way to do the problem, and a perfectly acceptable way to leave your answer. However, sometimes there are some, and if there are no instructions, just say simplify, you're done, full credit. But sometimes there are some rules that say leave no negative exponents in your answer. So, I got a problem. I got negative exponents here. So I use a rule. I use a rule that says this is the same thing as 13y to the 4th, but remember this is all over 1. I can take this x down using that rule from our note sheet. Take this x, which is x over 1, and reciprocate it. So now the x is in the denominator, and what do you do with the exponent? The exponent has to stay with the base of x, but you change its sign. Again, if there was no directions either way, both of these answers are acceptable. But sometimes your directions say leave no negative exponents. Sometimes there's problems that say there's directions that say leave no exponents in your denominator, so you just have to read very carefully. So I'm going to do this problem another way, just so you can see. I mean, 1001 divided by 77 is always going to be 13. But what if I chose to just move these down to the denominator from the very beginning? Right? I still have x to the 6 down there, and I move x to the, drop it, and negate the exponent. Then I can do the same with y to the negative 3, right? Y to the negative 3 is in the numerator. Drop it, and drop the negative. But do you know what, with this y to the negative 7? I can reciprocate 1 over y, can't I? Which means I can move that y to the top and negatize the negative exponent. So it becomes y to the 7th. So now look what happens. I have 13. I have y to the 7th over y cubed, which is y to the 4th. And then I have that x to the 6th, x to the 4th, x to the 10th. Wow. Same answer, right? So, lesson learned with negative exponents. What I think with negative exponents, I can take, well, what I think with any exponents, I can take any base I want and move it to a numerator or denominator as long as I change the sign on the exponent. So for instance, I could take, if I had x to the 3rd, y to the negative 2, z to the 10th, over a to the 4th, b to the negative 11th. If I want this x down in the denominator, I can take it here, drop it, negatize the exponent. If I want this a up the top, I can move it. I take the a, I take the exponent, but I negatize it. If I want this y to the negative 2 in the denominator, drop it, keep the base, but negatize it. It was negative 2, negatize it. I want b to the negative 11th in the top, I write b, I keep the 11, but change the sign on the exponent. I want the z in the denominator, I write the z down here, keep the exponent, but negatize it. Right? So you can move your base to numerator or denominator as long as the price you pay for that is negatizing the exponent. If it was positive, make it negative. If it was negative, make it positive. No. Was I done with that page? No, it wasn't. Ah! Okay. So, the next problem I put on here because I wanted to make sure you understood that none of our rules had C subtraction or addition in between. There's nothing for me to do with this except if they told me no negative exponents. If they said no negative exponents, the only thing I can do is keep the 7, take that x, Move it to the top and do what to the exponent? Change its sign. Keep that minus, write the 4. They said no negative exponent, so pop the x up to the top, do what with the exponent? It was a negative 1, so make it positive 1. And of course you don't have to write positive, you don't have to write an exponent of 1. And then you look, can you combine these two things? No, right? You cannot, they're not like terms, you cannot combine them. So, let's look at this one and attack this one like I was trying to scribble scrabble up there at the top. Firstly, this is the first thing that catches my eye. What is that? Any base to the 0 power is 1. 3 to the 4th, got to expand that. You can do that. 3 times 3 is 9, times 3 is 27, times another 3 is, 81. So, look at what I have here. I'm going to just practice with my negative exponent rules. I'm going to take that a to the negative 7th to the denominator, which means I have to make the exponent positive. I'm going to take the a to the negative 4th to the numerator, which means I have to make that exponent positive. Now I didn't have to. I could have just said see the base twice with division in between. That's a to the negative 7 minus negative 4, right? And I get a to the negative 3. I'm just showing you. I'm just doing it different ways. I like that b to the cubed where it is, but the b to the negative 5 I want to take to the top, which I can do as long as I change the sign on the exponent. I'm going to take that d with the negative exponent, the c to the positive 6 I'm going to leave where it is, and because it has a positive exponent, and d to the negative 4th I'm going to drop that to the denominator so that I can get rid of that negative exponent. So now notice I took a problem with a whole bunch of negative exponents. Now nobody asked me to, I'm just showing off. I took a problem with a whole bunch of negative exponents and turned them into a bunch of positive exponents, legally. What do I have from here? 81. See the same base twice. Now subtract 4 minus 7. It's a little more obvious that this should be negative 3. Then I have in the numerator, see the same base twice with multiplication in between. That's b to the 3 plus 5, which is 8. And in the denominator I have c to the 6, d to the 4th. There's nothing else to put together. So this answer is acceptable and perfectly legit unless somebody said no negative exponents. Then I would have to write my answer like this. Or if somebody said, so this is correct, this is correct if somebody said no negative exponents, or this is correct if somebody said leave no exponents in your denominator. Bring the c up, change the sign on the exponent. Bring the d up, change the sign on the exponent. Right? It just all depends upon my directions. And if nobody gives me directions, then I have to get full credit for any correct version. Last two. Alright, I have a negative exponent and I have fractionals. Alright, so I deal with numbers and letters differently. We are in the exponent and log unit, and we're doing exponents right now, which means no radicals in final answers. Only exponents. So even though I gave you that rule of fractional exponents being radicals, you can't leave any final answer with radicals. So when I look at this problem, now I see different bases with multiple exponents, so 64 to the negative 1/6 and x to the 2 times negative 1/6, which is negative 2/6, which of course is 64 to the negative 1/6 x to the negative 1/3. Now, I can leave, nobody said anything about negative exponents, so this part of my answer is just fine. But this is not. Right? That base is a number. I need you to evaluate this. And this is where that radical knowledge is going to come into play. So, first let's take care of the negative exponent. 64 is the base with a negative exponent, so put it in a denominator with a positive exponent. And then don't forget that you still have x to the negative 1/3 up here. Now, use radicals in the middle of your answer, not my final answer. Remember, this is a radical where the numerator stays with the base and the denominator becomes a 6. And now these are math problems and I'm not letting you have your calculator. So what this is asking you is, what integer can you multiply 6 times to get 64? And hopefully, it probably doesn't come to your mind right away, but I hope you think it's probably a small number. And sure enough, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, and times 2 is 64. That's the final answer. And if somebody doesn't want any negative exponents, that's your final answer. Okay? So I did use that radical property, but not for my final answer. Right? I only used it because I had a number. I used it to evaluate a number. I used the radicals, and I got an integer. If you don't get an integer, then like if 64 to the 1/6 had not been an integer, then that's when I can leave this alone. But if you need radicals to check to see if your numbers evaluate to an integer. Alright? Now, that was only part of this problem, wasn't it? This is 1 over 2x to the negative 1/3. I still have to do this part. So the next part looks like this. Remember, this has the first, see a bunch of bases with nothing but multiplication, distribute. So I get 32 to the negative 2/5 and x to the negative 10/5. So of course this is x to the negative 2 times 32 to the negative 2/5. Alright, so again, this is fine, unless somebody says no negative exponents, and they can know how to drop it down. But I have to evaluate this using my radical rules. So first thing, I can't do radicals with negative exponents, so the first thing I have to do is get rid of the negative exponent. And remember, I still have x to the negative 2 here. Now I have to turn this into a radical. So this is 32 squared. What? To the 5th. Well, that's terrible. 32 squared and then try to figure out some integer that multiplies 5 times? Watch this handy-dandy magic. Do you agree that I could, over here, rewrite this as 1 over, bye hun, 32 squared to the 1/5. Remember I talked to you about using properties backwards? This is really 2 times 1/5, isn't it? So I just wrote it that way. But isn't it true that multiplication is commutative? So can't I just do this? Isn't that still 32 to the 2/5? Convince yourself, right? See the base once with multiple exponents, you just multiply. That's 32 to the 2/5. But now I choose to Aunt Sally this, which means I'm going to ignore u square, and I'm just going to work with 32 to the 1/5. So I'm going to say this is 1 over, yes, radical, 32, but just with a power of 1 and an index here of 5. And now I can mentally handle this, right? Remember, I'm just ignoring the square out here. I can mentally handle this, whereas here I would have to square 32 with, now if I had a calculator, whatever, but I don't have a calculator. 32 squared? No, I don't think so. Now I just have 32 to the first. What number can you multiply 5 times together to get 32? Yep, that is 2. Now I'll listen to you, squared. What is 2 squared? So, what do I have? Remember, I still have x to the negative 2 here. So I have 1 times x to the negative 2 over 4. Right? And again, if I had to bring that down to the denominator, so I'm going to go up here and now say, what is this part? 1 over 4 squared. Oops, over here I wrote this wrong, didn't I? I dropped it to the, right? I had an x to the negative 1/3, so I brought it to the denominator and made it positive. Made the exponent positive. And then this is, and now I'm multiplying these two. So what do I have? The numerators are just 1. 1 over, what's 2 times 4? See the same base twice with multiplication in between. Write the base once and add. What's 1/3 plus, don't think of this as 2, think of it as 6/3. OMG. And of course, if nobody said anything about negative exponents, you could write your final answer this way. Phew! Now, this math trick over here, here's how I, instead of going through all of this nonsense, here's what I think in my head. I think to myself, when I get to this spot here, I say to myself, I do not want to square 32 and then think of the 5th root. So I think of osmosis. Osmosis means I'm going to take the square under the radical and osmosis it out here. Put parentheses and osmosis the square out there. Now, there's a proof behind it. I just did the proof. Right? I did this proof right here to show you why that works. But remember, I had a squared under the radical. I osmosised it outside so I could think of the 5th root of 32 instead of the 5th root of 32 squared. Sweet! Alright, last one. Here, this is really, remember, radicals. You can't have, this is the exponent unit. No radicals. So I have to unradicalize this. So what do I have? I have m to the 30th, k to the 32nd. That's all under a radical. But what is the index? 5. So you can get rid of the index by thinking that really is a denominator, and that's really a denominator on each one. Right, so this is m to the 30 over 5 is what? 6. K to the 32 over 5, which just leave because that doesn't reduce, so just leave it as 32 over 5. Okay? You could also think of this way. Which is what I started to do. You could think of all of this having an exponent of 1 on it. So you have m to the 30th, k to the 32nd, right? And the exponent of 1 is the numerator of the fractional power and the index is the denominator. But then of course you would distribute that and you would still get m to the 30 over 5, which is 6, and k to the 32 over 5. So either way, but this is what your final answer should look like, not this. If you can get rid of parentheses, you should. Alright? So that was a lot of Algebra 1 review, and then some Algebra 1 uglier, and then this handy-dandy math trick. Don't forget about that one. That comes in handy when I take your calculator out of your hand to evaluate fractional powers of integers, like this. Alright? That's all. So remember, I'm collecting that note sheet, and you have book homework to finish. For homework. See you tomorrow.